Welcome to this presentation about reinforcement learning. We are going to talk about offline reinforcement learning, in particular, what's possible to achieve with linear predictors, from exponential lower bounds to polynomial upper bounds. First of all, what is offline reinforcement learning? Well, you might be more familiar with online reinforcement learning. In online reinforcement learning, which is the standard reinforcement learning setting, there is an interaction between an agent and an environment. The agent submits action to the environment, and he receives next states and rewards. In the offline reinforcement learning setting, we assume this interaction has already occurred, and we are given a data set of state action rewards and next states. And then the data set, we are going to give it to the batch algorithm. And then we are going to ask questions to the batch algorithm. A typical question could be, for example, to extract from the data set a near optimal policy. There could be other tasks. For example, you can do policy evaluation. You can ask to evaluate the value of another policy, but for this talk, we are going to focus on extracting a near optimal policy. Now, we are going to consider the function approximation setting. In particular, we are going to assume that the action value function can be represented linearly as a linear product between a feature extractor that you do know and some parameter that is unknown to you, and you're trying to figure out the parameter. There are two parts of this talk. One is fundamental information theoretic lower bounds, which might be surprising if you're familiar with the statistical learning component. And then we are going to see what's possible to do if you add some extra assumption that is, I would say, an RL reinforcement learning assumption, in particular Bellman closure. And we are trying to see, we will try to see what's possible to achieve under those additional assumptions. So lower bounds. It turns out that realizability is insufficient in reinforcement learning. In particular, let's place ourselves in the best possible case. So let's assume we have no approximation error, the actual MDP as an exact linear representation for the optimal action value function. We are in the well-specified case. We are given a data set that is very explorative. In particular, it does cover in feature space pretty much every direction. And we are going to give you as much data as you want, even in the limit of infinite data. Now, if you're trying to just fit a linear predictor in machine learning, the answer here is trivial. There is no problem. I can recover the value of theta star. In reinforcement learning, unfortunately, well, it depends what you're modeling. If you're modeling the action value function, unfortunately, the problem turns out to be extremely complicated. And you can show a fundamental information theoretical lower bounds that says that even if you have this very strong assumption, perfect realizability, no misspecification, infinite data, very good conditioning, still you can find a class of MDPs where you can learn very, very little. Why is this even happening? Well, it's happening because somehow you can put some sort of neural network into your MDP, and the dynamics can be very complicated, and the action value function ends up being linear, but in reality, it is concealing a very complicated object, which is, in fact, a neural network. So this is not enough for learning. We have to add some extra assumption. Now, if you take a look at the RL literature, you're going to see a bunch of different assumptions. We are going to make one that is very reasonable, Bellman closure. I am now going to go into the details of this, but this is slightly stronger than realizability. Under this, you can start asking interesting questions. For example, what happens if I don't have a very good covariance matrix? For example, what happens if I don't have a lot of data in a certain direction, which might happen to be the direction of the optimal policy? What happens if I, of course, have a finite amount of data, and maybe those data they're being generated by some adversarial procedure, right? And maybe even maliciously. Well, under those conditions, we are able to create an algorithm that can find a very good policy with high probability, and it scales with the standard statistical rate, some quantity divided by square root of n. Square root of n is the amount of samples, and C represents the, I would say, the conditioning that you have about your problem. And this is just something specific to the data set. Let's delve a bit more into the algorithm. What's the goal, what's the setting, and what's the intuition for it? The setting is that we're going to give some data set to the bus algorithm, and we ask the algorithm to return a policy as good as possible, but with very high probability. So we want to be sure that the policy that is returned by the algorithm performs as advertised by the algorithm. Let me make a concrete example to understand the formulation. Concrete example is this. We have two policies A and B, and we want to find the best one to return. We have some available data. We are going to compute, for example, the empirical average of the return, and we want to return the one that is highest. But just knowing some empirical average is not going to be enough, because this could be wildly inaccurate. So second thing that we could do is try to construct some confidence interval with high probability, with the probability that you specify as input to your algorithm. And then you can start reasoning with those. And you could say, hey, I really want to be confident about what I return. And so I return policy A because, sure, it has a lower empirical mean, but I am way more confident. In particular, in a worst case scenario, the performance of policy A is going to be better than the performance of policy B. Now, if you spend 2-3 minutes thinking about this problem, which is very simple, I have just two actions, you will realize that I am solving really a max-min problem. I am trying to find the better alternative between A and B, and I am trying to see what's the worst case outcome for the alternative that I choose. Now, you can think about this in the sequential setting, in the reinforcement learning setting, and that's what we do for the work. We extend that intuition, and we design an algorithm that is able to pessimistically predict the value of different policies, and that's what we call a critic. And then we're going to couple it with an actor, and the actor is going to maximize over the policies. And this is, it has a nice framework because the critic is really trying to be adversarial compared to the actor, and it is using the data set, and it is trying to provide pessimistic evaluation to the policy that is selected by the actor. And so this is a classical, adversarial objective function. And what's the right tool to use for the maximization? Well, any algorithm essentially from online learning. Here we use mirror descent. And the whole procedure is what we call an actor critic method in reinforcement learning. And so in terms of main results, we discovered that really actor critic are a very natural way to solve a max-min problem in reinforcement learning, and somehow they are the natural approach to for learning from offline data in a very robust way. The procedure that we have happens to be minimax optimal. It is computationally tractable, and it has a bunch of other interesting things. More, future directions. Well, here we examine the linear setting. It would be nice to take a look at this and see what happens with more general function approximations. Another technical question could be, can we do the exploration counterpart? Can we try to leverage some of this idea in the exploration setting where I have to collect the data myself? And can I try to relax some of these assumptions that we make in offline reinforcement learning? And with this, I conclude, and I thank you for your attention.
Okay, time for one quick question while Angela sets up. Yeah, Philip.
So I think I missed one part. So this max-min formulation, you use it as your benchmark, or it's just a strategy to actually reach a more canonical benchmark for reinforcement learning?
It is basically the starting point of the algorithm. So we use it for constructing an algorithm. We solve this problem.
Okay, but the guarantee is not in terms of the subjective, is it?
The guarantee is going to be in terms of this objective. Yes, you have to, implement these things somehow, right? And so you have to speak about confidence interval, but yes, it will be in terms of this objective.
Thanks, Andrea. Next up is Angela.